A warm welcome, dear viewers. I am Dr.S.Saranya, Assistant Professor, PG and Research Department of Chemistry, Sithalakshmi Ramaswamy College, Tiruchirappalli. In this module, we are going to discuss about molecular rearrangement. In part 1, we will be discussing three rearrangements. So first let's see what is rearrangement. So rearrangement refers to the migration of an atom or a group of atoms from one atom to the another atom. The migration takes place within the molecule or from one molecule to the another molecule. The most common migrating atoms are carbon or hydrogen. But the migration of halogens, oxygen, sulfur, and nitrogen is also well known. A group may migrate to an electron deficient carbon or electron deficient nitrogen or electron deficient oxygen or to an electron rich carbon. The most important type of rearrangements involve one-two shift of alkyl or aryl group from one atom to the adjacent electron deficient atom. So now let us discuss about the rearrangements involving migration of a group to electron deficient carbon. So under this category, we are going to discuss two rearrangements. So the first rearrangement is pinacol-pinnacolone rearrangement. An acid catalyzed dehydration reaction involving rearrangement of 1,2 diols is called pinacol-pinnacolone rearrangement. So here you can see 2,3 butane 2,3 diol, that is pinacol, is treated with 30 percentage of hot sulfuric acid to give 3,3 dimethyl butane 2-one, that is pinacolone. Now let us discuss about the mechanism of this pinacol-pinacolone rearrangement. The first step is the protonation of the hydroxyl group. Since it is a symmetric diol, we can protonate any of the OH. So here this particular OH is protonated. So this acid makes this OH a good leaving group. So by the loss of a water molecule, a carbocation is generated. So in order to stabilize this carbocation, this methyl group is being shifted or migrated to this carbocation. So this is called as 1,2 shift. So now the positive charge is on the this carbon atom. So now the shift of this charge from the oxygen to the carbon leads to the formation of the pinacolone. So with symmetrical diols, there is no problem with the protonation and migration of the groups because this will lead to the same product. With unsymmetrical diol, the hydroxyl groups lost by protonation should be the one which leaves behind the more stable carbocation. So here you can see it is an example of unsymmetrical diol where two phenyl group is attached to one carbon and two methyl groups are attached to the another carbon. So now the protonation takes place at this point where the two phenyl groups are attached because this carbocation is stabilized by resonance. Further, the shift of this methyl group to this carbocation followed by the loss of proton leads to the product formation. So the first thing we need to remember is the carbocation stability. So what are all the remaining things we need to remember is the migratory aptitude of the substituents and the reaction condition. So all the three, carbocation stability, relative migrating aptitude of the substituents and the reaction conditions, they play an important role in the product formation. Next, let us look into the migratory aptitude. So in the case of unsymmetrical diols, aryl groups migrate preferentially in competition with the alkyl group. So it is very difficult to predict the migratory aptitude in the case of pinacol-pinacolone rearrangement. But this is the general order of the migratory aptitude. That is, aryl groups will have a good migrating aptitude compared to hydrogen, and this is more compared to alkyl. So these are all the applications of pinacol-pinacolone rearrangement. So benzopinacol in the presence of acid and iodine rearranges to form benzopinacolone. So the next example is the synthesis of spiroketones. So this can either be synthesized from this diol or it can be synthesized from this fused diols. The next rearrangement which we are going to see is the benzyl benzylic acid rearrangement. So alpha diketones, that is benzyls, they undergo base catalyzed reaction and is called as benzyl benzylic acid rearrangement. So here benzyl on treatment with potassium hydroxide followed by the acidification yields benzylic acid. So now let's discuss about the mechanism of benzyl benzylic acid rearrangement. The first step is the nucleophilic addition of this OH minus to this carbonyl carbon. So this leads to the migration of this phenyl group from this carbon to the adjacent carbon. This on further proton shift from this carboxylic acid to this oxygen will lead to a resonance stabilized carboxylate anion. So now an addition of a proton will lead to the corresponding benzylic acid. So these are all the various applications of benzyl benzylic acid rearrangement. The first example is the synthesis of citric acid. Various types of products are obtained using this benzyl benzylic acid rearrangement. So you can get ferulic acid, 9-hydroxy-9-fluorine carboxylic acid, and cyclopentanol 1-carboxylic acid. So now let us discuss about the rearrangements involving migration to electron deficient nitrogen. So previously we were discussing about the rearrangement involving migration to the electron deficient carbon. Now we are going to discuss electron deficient nitrogen. Under this, the rearrangement which you are going to see is the Beckmann rearrangement. So the rearrangement of oximes under the influence of a varieties of acidic reagents to form N-substituted amides is known as Beckmann rearrangement. So usually phosphorus pentachloride is commonly used as catalyst. So other catalytic reagents that are used for this Beckmann rearrangements are concentrated sulfuric acid, polyphosphoric acid, formic acid, thionyl chloride, silica are the various types of catalyst used. So here you can see the benzophenone oxime is treated with phosphorus pentachloride or any acid catalyst. It leads to the formation of benzanilide. Now let us look into the mechanism of this Beckmann rearrangement. The first step is the protonation of this OH group, which makes this OH a good leaving group. This leads to the loss of water molecule, formation of an iminocarbocation. The iminocarbocation abstracts the water molecule and thereby by the loss of a proton leads to the formation of N-substituted amides. The driving force for this 1,2 shift is the formation of the more stable carbocation. The Beckmann rearrangement is highly stereospecific, that is, the group anti to the oxime hydroxyl group always migrates regardless of the migratory aptitude of the two groups. For example, you can see here there are methyl as well as phenyl group. So methyl is present on the same side of this hydroxyl group, whereas the phenyl group is present opposite to the hydroxyl group. So methyl is syn to this oxime hydroxyl, and the phenyl group is anti to this oxime hydroxyl group. So the group that is anti will migrate efficiently regardless of the migratory aptitude of these two groups. So this is an acetophenone oxime. The phenyl group of this oxime hydroxyl migrates and the product acetanilide is formed. Another example is 4-bromophenyl methyl ketoxime. So this in the presence of H3PO4, it gives para-bromoacetanilide. So here the bromo substituted phenyl group that is anti to this hydroxyl group will migrate and it leads to the corresponding product. So these are all the applications of Beckmann rearrangement. So the first example is the synthesis of caprolactam. So from cyclohexanone oxime in the presence of sulfuric acid. Caprolactam under alkaline condition, it undergoes polymerization to give nylon. So these are all the various applications of this Beckmann rearrangement. So in all these examples, the group which is anti to the oxime hydroxyl will migrate and it leads to the corresponding products. Dear viewers, I hope you would have gained some knowledge about rearrangements. Thank you for your patience.